All right, looking at 8.4, I'll just say it now. 8.4, I would say, is one of the most difficult sections that you're going to see here in Calc 2. It's hard stuff, so I'm going to take my time here in the videos. 8.4 is for solving equations, or solving integrals, sorry, of something like this. So maybe dx over the square root of 4 plus x squared. Right now, we don't really have a technique for solving things like that, right? A u substitution is not going to work. Integration by parts is not going to work. There's no trig in it necessarily, although you'll see trig coming out of this. So it's just hard, right? So let me show you the way to go about doing this. This section we're going to call trigonometric substitutions. So like I said, trig is definitely going to come into play here. There are 3 different kinds of trig substitutions that you guys are going to do. All of these trig substitutions are based on right triangles. So if I have a generic right triangle, let's look at the right triangle that's kind of in the form that we have up top here. You want to think of this square root as being the Pythagorean theorem. So whenever you have 2 things that are added together, you can think of those like the 2 legs that are added together is equal to the hypotenuse, but we took the square root. All right. So this square root 4 plus x squared, we could make to be the hypotenuse. But instead of a 4, I'm just going to make this generic. We're going to do a squared plus x squared. So we're going to set the hypotenuse of a right triangle equal to the square root a squared plus x squared, which means that we could have an x as one of the legs and then an a as the other leg. Again, oh my God, I'm getting so many emails. Again, this means that that's Pythagorean theorem, right? X squared plus a squared would be equal to the hypotenuse squared, but of course we would just take the square root to get the hypotenuse itself. So if I let theta just be one of the angles here, then I can do a trig substitution of x based on theta. That trig substitution for this particular instance would be x is equal to a tangent theta. Okay, so again, if you ever have 2 things that are added together inside of a square root, your substitution is going to be x equals a tan theta. We would take this a little bit further, but I'm going to wait until we get into some examples to take this a little bit further. Let's at least just get all the substitutions written down. The other kind of example that you're going to see is if you have something like the square root of a squared minus x squared somewhere in your integral. If you have this somewhere, this is still Pythagorean theorem stuff, but this isn't going to represent the hypotenuse anymore. This is going to be representing one of the legs. So if you have this, we're going to put this down here as one of the legs. Doesn't really matter which one you put it as. We'll just stick it down here. Because the a is out in front, that means that's the bigger value. The bigger value has to be the hypotenuse, which means that this other leg is going to have to be x. Again, if I just let theta be one of my angles, I can do a trig substitution. For this theta, I have the opposite and the hypotenuse. Opposite and hypotenuse is sine. So the trig substitution we're going to do for this question, x equals a sine theta. All right, one other way that we could do it, that would be if we have the square root of x squared minus a squared somewhere in my integral. Again, we're going to make this to be one of the legs. I'll put it over here this time. Because the x is out in front, that has to be the bigger value. So that has to be the hypotenuse, and then the a has to be the leg. If I let my theta just be somewhere, for this one, I have adjacent, my a looks kind of funny, and hypotenuse, which would be cosine. It's just that it's flipped over this time. So instead of doing cosine, we're actually going to have to do its reciprocal secant. So the substitution x equals a secant theta. So these are the 3 main substitutions that we're going to look at. Of course, there's the other 3 as well, just based on how you draw your triangles. But these should be the only ones that you'll ever need. So if it's a squared plus x squared or x squared plus a squared, tangent. If it's the a, the constant out in front, sine. If the x is out in front of the subtraction, then secant. Okay, so let's look at doing an actual example. We'll just do that example that I have up above there. So we're going to look at the integral of dx over square root of 4 plus x squared. All right, we already decided that tangent is going to be the substitution we're going to do. But there's a little bit more to it than just writing that substitution. We're going to have to not only substitute out the square root 4 plus x squared, but we're going to have to substitute out the differential as well. So let's write it out. We're going to do the substitution by letting x equal to 2 tan theta. It's going to be a 2, right, because it's always the square root of the constant. That's a squared, which means my a is 2. Not only is this going to come into play, let's go ahead and figure out what 4 plus x squared is. That way we can substitute it in directly. So if my x is 2 tangent theta, and I substitute that into 4 plus x squared, I'm going to get 4 plus 2 tangent theta squared, which is 4 tangent squared theta. What I can do here is I can factor a 4 out of that, and then I get 1 plus tangent squared. This is a Pythagorean identity that you should recognize. 1 plus tangent squared is the same thing as secant squared. So eventually, when we do the substitution, this 4 plus x squared, I'm just going to replace with 4 secant squared. There's one other thing we need to worry about, and that's the differential up top, this dx. So let's go ahead and figure out what that is as well. You do this the same way you do a u substitution. So if x is 2 tangent theta, then dx is going to be the derivative of 2 tangent theta, which is 2 secant squared theta. Do not forget to put the d theta on the end. Okay, now we have all the substitutions that we need. We can plug them all into my integral. So now my integral is going to be dx, where dx is 2 secant squared d theta, divided by the square root of 4 plus x squared, where 4 plus x squared is 4 secant squared. Okay? I have a 2 up top and a square root of 4, which is a 2 in the bottom, so my constants just disappear. I have a secant squared up top, and then the square root of secant squared, which is just 1 secant on the bottom, so secant squared divided by secant is just a single secant. Okay, the integral of secant theta d theta, is on that integration table. So go to the integration table that I gave you guys, look up the integral of secant. This ends up being the natural log of the absolute value of secant plus tangent, plus c. Okay. But we are not done, right? This is the antiderivative, but this is the antiderivative in terms of theta. Our original integral was in terms of x. So I need to substitute out the thetas for x. And we're going to do that using our substitution equations over here. I need to figure out what secant theta is in terms of x, and I need to figure out what tangent theta is in terms of x. As far as secant goes, I do have an equation that has secant in it right here. I can solve for that secant by dividing the 4 all the way to the beginning and then taking the inverse to get the theta by itself. Oh, no, I don't have to do the inverse, sorry. I'm looking for secant theta. We need to take the square root to get just secant theta by itself. So let me come down here. This is kind of over in scratch paper. What I had up top there was 4 plus x squared was equal to 2 secant squared. No, it was 4 secant squared, wasn't it? Sorry about that. 4 secant squared. So we're going to divide the 4 over. And then we're going to take the square root. When we take the square root of this fraction, we're going to take the square root of the top and the square root of the bottom separately. So we get the square root of 4 plus x squared all over 2 is equal to secant. So that I can just plug right into my antiderivative. The natural log of secant, which is now the square root of 4 plus x squared all over 2. Plus tangent. So let's go back up to my substitution equations. Oh, there he goes. So tangent comes from this equation. X equals 2 tangent theta. So if I just divide the 2 over, I get x over 2 is equal to tangent. which means that in my antiderivative here, tangent, I could just substitute with x over 2. Okay, so we get our antiderivative, and I know it looks awful. The natural log of the absolute value of the square root 4 plus squared, all divided by 2, plus x over 2, all of that plus a constant. But I promise you, if you were to take this and find the derivative of this, the derivative of that would come out to be 1 over the square root 4 plus x squared. All right, I have plenty more examples of this, so I'm going to make one more video probably, just doing some examples.